capacity of a channel affected by fading. Remember the fading model that we have. Fading model assumes that the received signal is given by the transmitted signal multiplied by a random variable capital R plus noise. We have originally assumed ergodicity, which means that the code words are long enough to experience essentially all the possible values of attenuation R, and consequently we have an averaging effect included in each code word. Under these conditions, we have computed the capacity, the ergodic capacity, the expectation of the logarithm of 1 plus R squared signal to noise ratio, based on the fact that once we have our fading channel model, the signal to noise ratio of editing wide Gaussian noise channel becomes R squared signal to noise ratio, and then we have the computation, the expectation due to the ergodicity effect. So this is the basic result. Given the probability density function for the model of fading that we are assuming, we can get the capacity that we want. And we have seen some results. The most interesting among them being the fact that the difference in capacity between additive wide Gaussian noise channel and the Rayleigh fading channel is relatively small, especially if compared with the big difference that there is in terms of error probability. Okay, now we have to evaluate what's going on when the ergodicity assumption is not valid anymore, and we have to consider non-ergodic channel. Things change quite a bit, and it's important to understand what's going on when the ergodicity assumption is lost. Let me consider a very simple example of an non-ergodic channel. Remember, one of the basic assumptions of the leading to ergodicity is the fact that fading changes fast enough so that a code word experiences all the states of the channel. Now, let's consider a very simple example of, well, probably the simplest possible example of a non-ergodic channel. We have two additive wide Gaussian noise channels characterized by different capacities. The first channel has a capacity of 1 bit per channel use, and the other channel has a capacity of 2 bits per channel use. We transmit a code word, and the random switch selects one of these two channels, and the selection remains the same for the whole transmission of a code word, which is in a sense in a limiting case of a channel that is very slow, so slow that it doesn't change during the transmission of a code word. And the fading effect translates into the effect of this random switch. So the random switch unknowingly, I mean the transmitter doesn't know the position of random switch before transmission. The random switch selects one of the two channels. So this is a very simple example of a fading channel in which we have two fading amplitudes. Okay? The basic difference between this and the ergodic channel that we had considered before stands in the fact that instead of changing from symbol to symbol, the channel remains the same for the whole transmission of a code word. Okay, what is the capacity of this channel? Well, a naive answer, and wrong answer for that matter, a naive answer would be, well, if the random switch for 50% of the cases of the code word is in the upper position, and for 50% is in the lower position, would make the capacity to be the average between the two. So this is capacity 1, and this is capacity 2, so the capacity would be 1.5. Well, the answer is wrong for a reason that we are going to see in a moment. In fact, if we transmit at rate 1.5, suppose that the capacity is really 1.5. So the meaning of the capacity is that if we transmit at a rate slightly lower than 1.5, we can achieve an error probability close to 0. However, if we transmit at a rate close to 1.5, then for 50% of the time, 50% of the code word, we meet the channel with capacity 2, which is fine, and consequently the error probability is 0. But for 50% of the code words, the channel met, it has capacity 1. we are transmitting with rate 1.5 over a channel with capacity 1, and consequently the error probability will be 1. Okay? So what's the overall error probability? Very high, and definitely not 0. So we cannot transmit at rate 1.5, which means that the channel capacity is not 1.5. To be able to transmit with error probability 0, we should transmit at rate close to 1, slightly smaller than 1. Okay, so this is the maximum rate at which we can transmit with vanishingly small error probability, 1. So that's the channel capacity. So in this channel we have a capacity equal to the smaller capacity, smaller between the two capacities here. Now let's consider a real fading channel in which the fading variable, the R, the channel state, remains the same for the whole transmission of a code word. Okay? And we have an infinite number of them. What is the capacity? The capacity would be the capacity of the the worst possible channel, because this is the rate at which we can transmit with vanishingly small error probability. Okay? Worst case occurs when we transmit our code word on the worst channel. Okay? And that's the capacity of the channel. Now, let's consider a Rayleigh fading channel. So let's do the calculation. What is the capacity for a Rayleigh fading channel? We do the calculation based on this conceptual framework, and we discover that the capacity is 0. So there is no positive rate at which we can transmit such that the error probability is 0. What does it mean? It means that we cannot transmit on the Rayleigh fading channel. Clearly not. The point is we have to redefine capacity. We need a new operational definition of capacity based on the fact that on a Rayleigh fading channel we can never have the certainty that we transmit a code word. The code word is affected by the same fading and we get an error probability 0. Yes?
For the Beer's definition of capacity,
yes.
You can use whatever transmitter you want, right?
Whatever?
Transmitter you want.
Well, to achieve capacity, we have to use an optimum code.
Yes, but so the capacity is the maximum rate at which you can transmit.
At maximum rate at which you can, provided that you are able to generate an optimum code.
Doesn't this flexibility on choosing the transmit strategy include memory, for example?
Well, we are talking about memoryless channels basically here, so we are not considering the.
Not channel memory, but you could store bits at the transmitter.
Mm-hmm.
I mean, the switching case, even though the rate at which you produce data is 1.5, you
yes.
could actually store these bits at the transmitter and shoot out 2 bits or 1 bit according to which channel.
But you don't know. The transmitter in this case doesn't know the state of the channel. That's the basic assumption. If it knows it, there are several possible strategies, but we assume that the channel state information is not available at the transmitter. Okay, so we need a new operational definition to bypass the problem that if we accept the usual definition of capacity, the maximum rate that we can transmit for reliable information is 0. Okay, so let's define this quantity, and then we're going to discuss them. Define an instantaneous mutual information. Instantaneous mutual information is the mutual information at which the channel can accept. I mean, the amount of information that the channel can accept at any given time. That depends on the instantaneous value of the fading. Okay? So if the fading attenuation is R, then the instantaneous mutual information is C of R. That's the logarithm of 1 plus R squared signal-to-noise ratio. Now, let's define an outage probability. This is the probability that the rate of our channel exceeds the instantaneous mutual information. So when this occurs, that is, when we are transmitting at a rate that exceeds the instantaneous mutual information, remember we are talking about long code words and channels that remain in the same state for the whole duration of a code word. Okay. We have an outage. So we are transmitting at rate R. The channel cannot transmit at that rate, and consequently we have an outage. We lose information. We have a very high error probability, which means that the whole code word will be lost. The loss of code word is referred to as an outage. and the outage probability is the probability that we are transmitting at the rate that cannot be supported by the channel at that instant for that channel state. Okay, so let's combine together these two definitions. And let's define what is called outage capacity. The outage capacity is the maximum rate at which we can transmit once we decide that we can tolerate a certain outage probability. So that's the outage capacity is the maximum rho such that we achieve the outage probability that we can tolerate. For example, let's tolerate an outage probability of 1%. That means that for 1% of the time, 1% of the code word, the whole information included in the code word will be lost. For 99% of the time, 99% of the code word, we can achieve a zero error probability, and the rate at which we can do this is called the outage capacity. Okay? For standard, for ergodic channel, the outage capacity is 0. So there is a rate that we can transmit such that all code words have an error probability which is vanishingly small. In the case of a non-ergodic channel, we must accept an outage probability because otherwise the capacity will be 0. So we accept a maximum rate that we can transmit, at which we can transmit information over the channel with a given pre-assigned outage probability. Okay, so that's the difference between ergodic channel and non-ergodic channel. Capacity in an ergodic channel means the rate that we can transmit with vanishingly small error probability. With a non-ergodic channel, is the rate that we can transmit with vanishingly small error probability, provided that we can accept that a certain percentage of code word will be lost. So, for example, let's consider the outage probability for a non-ergodic Rayleigh fading channel, one in which the R remains constant for the whole transmission of a code word. So this is the what we have. The ordinate is the outage probability, and abscissa is the rate that we can transmit bit per dimension pair. So we accept a outage probability, let's say, of 10%. Okay, so we consider this. And these are the corresponding abscissas are the rate that we can transmit. The rate is obviously higher if the signal-to-noise ratio is higher, or higher is if the outage probability, the admitted outage probability is higher. So this is what we get, actually, 0.10%, for example, which is a reasonable number. And this is the rate at which we can, maximum rate at which we can transmit, consequently the outage capacity with a predefined outage probability value. Our channel, practical channel, ergodic or non-ergodic? Well, that depends on the parameters of the channel. In particular, it depends on the coherence time of the channel. Remember, coherence time is the time in which two time components, or two symbols if you prefer, are affected by the same fading. So if we have a very long coherence time, that means that the symbols in a code word are affected essentially by the same value of attenuation. Consequently, you have a non-ergodic situation. For ergodicity, we need a very short coherence time. So that's symbols, adjacent symbols are affected by independent values of fading. So let's see a typical example with Doppler spread corresponding to reasonable velocities going from 1 to 100 hertz, and consider a transmission rate from ranging from 20,000 kilosymbols per second to 2 million symbols per second. Okay, coherence time is the inverse of the Doppler spread, so the coherence time ranges from 0.01 to 1 second. So the fading has about the same value for this whole duration. The fading has about the same value for all symbols transmitted in this time period, 0.01 to 1 second. So for this velocity, we have 200 symbols affecting So for this transmission rate, we have 200 symbols affected by the same fading. For this transmission rate, we have 2 million symbols affected by the same fading. That means that if this is the situation, whatever code word whose length is less than 2 million symbols will be affected by one and the same value of fading, and consequently the non-ergodic channel model applies. Consequently, if we have a fade or a deep fade, this affects the number of symbols that is proportional to the coherence time. And the situation is pretty bad because whatever code you use, the common code is not usually designed in order to be able to correct very long bursts of errors. Codes are usually very good when it comes to correcting isolated errors, but if they are long bursts of error, there is nothing you can do about it, and performance is definitely degraded. So if we want to decrease the coherence time, what you can do? How can you design a code like that? Usual codes are not adequate in a situation when you have a very long coherence time. On the other hand, the coherence time may be very long if the motion is very slow, or the user is stationary, and the transmission speed is very high. What you can do in this case? Well, you want to decrease the coherence time without acting on the physical aspect of the channel. And a simple way of doing this is they use interleaving. Interleaving is actually, in this context, is an operation whose aim is to decrease the coherence time. This is the common solution in wireless systems. So we can think of interleaving as a way of decreasing coherence time. There's another interpretation of coherence time that we are going to see tomorrow that has to deal with the iterative algorithm. But for the moment, interleaving is something that decreases the coherence time and consequently breaks the memory of the fading. So this is a very simple example of interleaving. It's called block interleaving. The idea is the following. We have a matrix. Here, a very simple example. We have a matrix with 4 rows and 8 columns. So we have 32 symbols here. And the symbols are written row-wise, sequentially, from the source to the channel, okay, in this matrix. So we write the symbols row-wise from x1 to x32. And then we send them through the channel by reading from the matrix column-wise. So we send x1, then x9, then x17, then x25, then x2, and so forth. So in a sense, we scramble the symbols. We change the order in which the symbols are transmitted. So let's suppose, again, in a very simple situation, that this is the sequence of symbols entering the channel. And let's suppose that the coherence time of the channel is such that 3 adjacent symbols are affected by exactly the same fading value, right, over the channel. When we de-interleave, and we de-interleave simply by doing the reverse operation, that is writing column-wise and reading row-wise in order to reconstruct the original flow of the data. After de-interleaving, we see that the fading values that over the channel affect adjacent symbols here affect symbols that are not adjacent anymore. They are separated. Consequently, if the interleaving depth is large enough, we can think that the symbols are belong to different code words, and consequently we don't have the non-ergodicity effect that is disturbing us. So we have transformed a burst of errors into isolated errors. And the channel becomes close to an ergodic channel if we need that. So in other words, we can think of interleaving as an operation transforming a channel with memory into a channel without memory. So if this is the channel model, multiplication by R and addition of noise, such that R are correlated, in the limit they are the same value for all code words, for the whole duration of a code word. If we introduce this interleaver and the de-interleaver, we transform the equivalent channel into one without memory, or with the memory considerably reduced. so that the channel becomes close to ergodic or ergodic. So interleaving reduces the coherence time by destroying the channel memory and consequently improves performance when we are using coding. There is a downside to interleaving though. Interleaving introduces delay. Actually, before we are able to transmit over the channel the sequence, we have to fill up this matrix. And consequently, at the receiver, we have to fill up a similar matrix in order to recover the original order of the symbols. All these operations take time. These are information lossless, of course, but they takes time to do it. And consequently, we add some latency in the system. And this delay or latency may not be tolerated. Real-time communication, speech communication, for example, we may not be able to tolerate a delay beyond, let's say, 100 milliseconds or something like this. For television transmission, there may be no problem. 1 second delay in a transmission of a TV program may not be a big deal. But in interactive communication, a large delay may not be tolerated. And consequently, we might not be able to introduce interleaving to the depth that is necessary to transform the channel into an ergodic channel. So we have a number of intermediate situations that we would like to take into account. Intermediate situations that occur whenever you would like to have to remove the memory in the channel, but you cannot because of the delay constraints. So for a delay constrained system, we have to consider the possibility of having a non-ergodic channel. Okay, let me, I have already discussed that. Let me now evaluate the error probability when we have coding in a fading channel. So remember that the calculation of error probability is based on the calculation of pairwise error probabilities. It is the probability that the received signal is closer to x hat than it is to x when x was transmitted. Then we condition the overall thing with respect to the random variable representing the fading. Notice that here R is in boldface because R is a matrix, is a diagonal matrix whose components on the main diagonal correspond to the coefficients that affect each component of the vector that we transmit. So we transmit a vector x with a certain number of components, and each component of x is affected by one component of R. So R multiplied by x is represent the actual vector in which every component is affected by a different value of fading. Okay? So with coding, we have to modify our calculation by taking into account the fact that R is now a diagonal matrix. We don't have to do many calculations because we already know what the result is going to be. The pairwise error probability without taking R into account is Q of norm of x minus x hat divided by square root of 2 and 0. When we have R multiplying x, what we have to do is just to take the product of R and x in the formula. No more, no less than that. Again, we can upper bound the Gaussian tail function Q using an exponential. So instead of doing the exact formula that is hardly amenable to a closed form when we take the expectation, we take the upper bound here. Okay, so this is pairwise error probability conditioned on a certain set of fading values. Now, assume that the components of R are independent. So we are considering an ergodic channel or a channel that was made ergodic or almost ergodic by interleaving. Okay? So we assume that the components of vector of matrix R, diagonal matrix R, R1, etc., Rn, are independent. Okay? And the length of the vector x is n. Okay, so if we rewrite this inequality by expressing the components of R and the components of X, we have to take the expectation of this exponential. Fine. Now we use the assumption of independent values. So this expectation made with respect to all these random variables is the product of the expectation taken with respect to each one of the random variables. So the expectation of this turns out to be a product of expectations, each one involving one of the components of the fading. If we compute this expectation in the assumption of Rayleigh fading, we end up with this formula. So the probability, the pairwise error probability, is upper bounded by an expression like this. Okay, so this is the starting point. Let's elaborate on this formula in order to get some extra insight of what happens when we transmit a code word over the fading channel, in particular the Rayleigh fading channel. We are focusing on the Rayleigh fading channel because of its importance as a kind of worst case, and also because it's amenable to closed form expressions. Now, let's return this, okay, vector x and vector s hat, and this this pairwise error probability is expressed in terms that make clear the role played by each one of the components. Okay, let's assume that x and x hat differ in a certain number of positions. There are n components. We have two different vectors, and they may or may not differ in all positions. Certainly at least one position. The number of positions in which they differ is called the Hamming distance, no more, no less than the Hamming distance that is at the basis of the definition of algebraic coding theory. The Hamming distance, anyway, is the number of positions in which two vectors differ. Okay. Let's define this set I in which their positions differ. For example, if they differ in the first and second position, I will be 1, 2. Okay, the set of 1. Okay, so this is the result we have obtained. We observe that the error probability here, okay, can be upper bounded by a term and by a product in which we have removed this constant, this 1, but we must be careful in this case. But be careful, because if we remove this and we end up with a term whose component xi is equal to x hat, this will be 0, and consequently the ratio will be infinity. So if we want to remove this using a bound that simplifies the expression, we must make sure that in this product we keep only into consideration the terms that have xi different from x hat I. Here they have no contribution, because if this difference is 0, then we have a contribution 1 to the product, so the term can be disregarded. But if we remove this term 1 plus, then we have to disregard from the beginning the indices such that xi is equal to x hat I. Okay, so we do this. We remove this 1 plus term, so further loosening the upper bound. And then we consider the product extended only to the positions in which the two code words differ. Okay, once we have this expression, we may isolate two terms. The terms 1 over 4 and 0, which is proportional to the signal-to-noise ratio. And this is raised to a power equal to the number of terms in this product. The number of terms in the product is the Hamming distance. So we have 1 over 4 and 0 raised to the power dh of the Hamming distance. Sorry, this is not a minus, this is a plus, actually. And the other term, it takes into account the product of these xi minus x hat I extended to the set of indices in which they differ. Okay, this dh is called the code diversity for a reason that depends on the concept of diversity in wireless transmission, and a concept on which I shall return. Anyway, for the moment, let's take it just as a definition. The Hamming distance between x and s hat is called the diversity of the code. So we have a pairwise error probability that is bounded above by signal-to-noise ratio raised to a power equal to the Hamming distance of the code and multiplied by a factor that depends on the product of the components in which the two code words differ. So that's the basic result. That's interpreted.
So where's the energy per bit?
Pardon?
Where is the energy per bit? You said that's the signal-to-noise ratio, but that's only the noise.
No, I didn't get the question, sorry.
Where is the energy per bit?
Well, the energy per bit is essentially contained in this term. Because xi are the symbols, and they each one of them has a certain energy. So we may include the energy here, or we may remove the energy here and bring it this way. But the important thing is that this, being inversely proportional to the power spectral density of noise, is proportional to the signal-to-noise ratio for a given set of energy of the signals. So this tells us what happens when we decrease the decreased noise, and consequently, it said that the error probability will have a slope that depends on the Hamming distance. This is interesting because for additive wide Gaussian noise channel, when we have a code, we know that the error probability depends on the Euclidean distance, the minimum Euclidean distance between two code words. In Rayleigh fading channel, for high signal-to-noise ratio, the error probability depends on the Hamming distance. The Hamming distance and Euclidean distance may be linearly related, but also may not be. Okay, for binary modulation, the two are related. Hamming distance is the same as Euclidean distance, proportional to Euclidean distance. For other constellations, for example, 8 PSK, the two things are not related. And consequently, the criterion of optimality for Gaussian noise, which is the maximization of the Euclidean distance, is not the same for Rayleigh fading channel, at least for high signal-to-noise ratio. In this case, we should optimize the Hamming distance rather than Euclidean distance. And this is what this formula says. This formula leads to some strange results and to a couple of facts that I'm going to discuss. For example, consider these two constellations. These are 4 PSK and they're rotated 4 PSK. The minimum Hamming distance of this constellation is 1. If you write down the components of this, you see that, for example, this will be, say, +1, +1, and this is +1, -1, which means that the two vectors have differing one component. So the minimum Hamming distance of this constellation is 1. If we take the same constellation and rotate it by a certain amount, then we discover that the minimum Hamming distance is 2. If we take the coordinates of each one of these points in the 4 vectors, you discover that no two vectors differ in just one component. All vectors differ in 2 components. So we have Hamming distance 1 and Hamming distance 2. Well, if you transmit these 2 constellations on the additive wide Gaussian noise channel, you end up with the same error probability, because a basic fact, which is well known in digital communication, is the fact that any rotation or translation, etc., of a constellation in the space does not affect the error probability in the Gaussian channel because of the specific symmetry property of the Gaussian density function. But on the Rayleigh fading channel, these 2 constellations will have different error probabilities, because on the Rayleigh fading channel for high signal-to-noise ratio, the error probability depends on the minimum Hamming distance. Consequently, this one will be worse than this one. And in fact, we can see what happens if we have a deep fade affecting, let's say, just one of the signal components. Okay, let's assume that we transmit the 2 components of 2 independent channels, and one is affected by a deep fade. Right? So one of the amplitude is destroyed. So in this case, it means that the 2 dimensions collapse into one. The amplitude of the second component is brought to 0. And this is what happened to this constellation on a deep fade affecting the second component. We lose 1 bit, because from 4 potential signal, we are reduced to 2. 2 signals collapsed into 1. So we lose 1 bit. In this case, if the second dimension collapses, we still have 4 separate signals. The distance is reduced, and the Euclidean distance is reduced, but we don't care. The important fact is that we have a better performance because we don't lose 1 bit. So this is one of the strange things that happen with this model, that things that happen in Gaussian noise may not happen in Rayleigh fading channel. And the wisdom that we have accumulated in our study of additive wide Gaussian noise may not be valid in a Rayleigh fading channel. So we can take a constellation, in the basic idea, and somebody has actually done this exercise, taking a standard constellation and rotating in the multidimensional space until you get the best possible performance in terms of error probability on the fading channel. And the best possible performance is achieved when you maximize the Euclidean distance. Now, given this, let's see what happens once we cannot assume that we have ergodicity. So far, this calculation that has led to this fundamental result, this one, was based on the assumption of independence of the fading components. So this calculation is valid when R1, etc. are independent. So adjacent symbols are affected by independent values of fading. What happens if this is not a realistic assumption? And it's not a realistic assumption whenever we are not able to do deep enough interleaving because of our delay constraint. So what happens if we have a delay constraint system? What happens to the error probability? Again, assume that we transmit a code word with length capital N, and in order to have each symbol affected by an independent fading gain, we should do interleaving. How deep the interleaver should be? Well, if we have a channel such that L adjacent symbols are affected by the same fading gain, and we want every symbol in a single code word to be affected by an independent value of fading, then the time span of the interleaver should be at least n times L, the length of the code word multiplied by the number of symbols affected by the same fading gain. Remember, L can be very large, hundreds of millions, to some hundred to some millions of symbols. And if the code word is very long, then you see that it's not tolerable to have to design an interleaver this deep. So because the delay would become very large. So this is a measure of the delay that we should introduce if we want to do perfect interleaving with code words of length n and coherence time of the channel size that L symbols are affected by the same fading gain. Okay, so what do we do in this case? Well, we change the model of our system and we compute again the error probability. The model that we can assume in this case is a so-called block fading model. The channel becomes a block fading channel. It means that when we have a code word, we can split the code word into sub-blocks, and each sub-block is affected by the same fading value. The two limiting cases are ergodic channel. Each symbol is affected by an independent fading. The other limiting case is non-ergodic channel, in which the whole code word is affected by the same fading gain. In between, there is the block fading channel model, in which the code word is divided into sub-blocks, and each one of them is affected by one fading gain. So this is the situation. The code is given by, the code word is given by the whole set of symbols, that capital N symbols, and new adjacent symbols are affected by the same fading value. And F is the number of blocks. So this model is equivalent to having F, capital F, independent channels, each one being affected by an independent value of fading. Okay? if there are two limiting cases that are reflected by this model. F equal to 1 means that the whole code word is affected by the same fading gain. That's the limiting case of a non-ergodicity. Or F is equal to n, which means that each symbol is affected by an independent fading gain, ideal interleaving. In between F equal to 1 and F equal to n, we have a number of intermediate cases that corresponds to different delay constraints. Okay? Between every symbol being affected by independent fading and all code words affected by independent fading, by the same value of fading, we have intermediate cases. Okay. One possible value, two possible values of fading, 3, 4, etc. And each one of them corresponds to a delay constraint. No interleaving means a maximum delay constraint. Ideal interleaving means no delay constraint. What happens to error probability when we are forced to transmit on a block fading channel model? Well, first of all, is this a reasonable assumption for a good model? Well, for example, GSM with frequency hopping divides the code word into 4 blocks, and each block is transmitted in a different slot comprising a certain channel, certain frequency, and certain time. So with frequency hopping, we may have a code word transmitted through 4 independent fading channels. Consequently, we have a block fading channel with F equal to 4. On IS-54, another standard, with time hopping, the code word is divided into 2 sub-blocks, and each block is transmitted on a different time slot, and the time difference between the 2 slots in which we transmit the first half and the second half of code word are separated by at least the coherence time of the channel. Okay? If this is the coherence time, then we transmit this and the second part of the code word after the coherence time, and consequently 1 and 2 will be affected by 2 independent values of fading. So it is another case in which the block fading model is appropriate. What happens to the error probability? Well, we can repeat exactly the same calculations as before, where instead of symbols we have blocks of symbols. So formally the calculations are the same, it's that the interpretation is different. Let's take a look at the previous result, where we have symbols that are affected by independent values of fading. In this case, instead of symbols affected by independent values of fading, we have small blocks affected by independent values of fading. So instead of xi, we'll write a block included in the code word. So this is the result that we get, which is formally identical to the result with an ergodic channel model. Oh, here it is. So we transmit the code word X, the pairwise probability of a receiver preferring S hat to X is upper bounded by this expression. The product distance as before, signal to noise ratio as before, but now the most basic difference between the previous formula and this one is that instead of the Hamming distance between two code words, that is the number of symbols in which the code words differ, we have the number of blocks in which the two code words differ. Remember, symbols, blocks, symbols in the ergodic model, blocks in the block fading models. So we have the so-called Hamming block distance, the number of blocks in which they differ. So the diversity, the exponent of the error probability, again this is a plus. No, sorry, no, I take it back. No, this is a minus. Sorry about this, sorry, minus. Signal to noise ratio is a denominator. This depends on the number of blocks in which they differ. So the slope will depend on the number of blocks in which they two code will differ. Let me see a couple of examples to see how things go. So the code diversity, I mean the term that tells you what is the exponent of signal to noise ratio with which the error probability decreases, is the Hamming block distance. Example. let's consider the two code words, a code word with plus and a code word with a certain number of minuses. So what is the pairwise error probability between these two code words? Okay, we have to consider different situations according to the kind of delay constraint that we have, and consequently the amount of interleaving that we can introduce. If we have full interleaving, then each symbol is affected by a different independent value of fading, and consequently the error probability will depend on the Hamming distance. So the number of components, the number of symbols in which the two code words differ. We count them, 1, 2, 3, 4, 5, 6, 7. So the exponent will be 7 in this case. The best situation that we have. Signal-to-noise ratio raised to power minus 7. Next, let's suppose that we have some delay constraint. This means that we have the possibility of splitting the code words into 8 blocks. Each block is affected by an independent value of fading. So a certain amount of interleaving is possible here. Now, what is the performance? Well, the performance will be determined by the number of blocks in which these two differ. So we have to consider the yellow blocks and count how many of them are include different pairs. So that's 1, 2, 3, 4. These are the same. These are the same. 5 and 6. So the block Hamming distance will be 6. So if we are not allowed to do full interleaving, but we are allowed to do some interleaving such that two adjacent symbols are affected by the same fading value, then we decrease the quality of our system, and the error probability will depend on signal-to-noise ratio raised to power minus 6 instead of 7. Further delay constraint. We have 4 blocks. We divided this into 4 blocks. How many blocks they are in which first code word and the code word differ? That's 1, 2. These are the same. 3. So the Hamming distance decreases to 3. 2 code words, which means that 2 code words with block length 8, which means that our delay constraints are very strong, so we are not able to do better than this, so that the code word will be affected by 2 independent value of fading. These are differ, so d2 is equal to 2. And finally, if we are not able to do interleaving, then the Hamming distance is equal to 1. Okay. So this is the situation. Typically, we decrease the block Hamming distance as we increase the constraint in the system. No interleaving to full interleaving. And you see that exponent of signal-to-noise ratio is a very important parameter because it determines the slope of the error probability curve. And we want the slope to be as steep as possible. Another example of a code. This is a convolutional code divided into blocks with length 4 symbols. Okay? Let's assume that this is the reference code word corresponding to this path, and this is the received code word. In this case, the minimum Hamming distance would be equal to 2. So we reduce the Hamming distance to a block Hamming distance, and consequently we reduce the quality of the transmission over the fading channel. So this explains how the delay constraint reduce the performance of the system. This is the singleton bound that tells us what the maximum value of the minimum block distance. That depends on f. Remember, f is the number of blocks in which can divide the code word in order to have f independent values. The maximum value of f is the number of symbols in the code word. The minimum value is 1. 1 minus rate of the code divided by logarithm of capital M. M is the size of the elementary constellation. We see that from this formula that the worst possible value of M is equal to 2. if we increase m, we can increase the upper bound to the block Hamming distance and consequently to the code diversity. So binary modulation is the worst we can do in a block feeding channel. And an interesting application of this formula is the following. This is the rate 1/2 convolutional code that was standardized for using GSM, a GSM that has f equal to 8, and the free distance of this code is 7. This is the Hamming distance that we have in the case of ergodic channel, when we don't have any delay constraint. However, we have delay constraints, which are reflected by the fact that the code will have f equal to 8. This code was chosen among many with the same rate by simulating their performance on a certain set of channels that are standardized in the description of GSM. Let's see that this, and this was not known by the designer at that time, let's see that this code is actually optimal in the sense of maximizing the block Hamming distance for f equal to 8. In fact, for f equal to 8, if we apply the previous formula, we see that the f equal to 8, the binary constellation and rate 1/2, we have that d is less than or equal to 5. Okay, it can be proved that this code has actually the mean is equal to 5, so the theoretical maximum is 5. This code achieves 5, and consequently we can say that this code is actually optimum from this optimization criteria. Without doing any simulation, we can just reduce our consideration to codes that can achieve the upper bound to the block distance. Okay, so this is what I could say about the general performance of a coded scheme over the feeding channel. The interesting thing, that the main lesson that we have to learn is that we have to consider very seriously what is the coherence time and the coherence bandwidth of the channel in order to appreciate what the effect of the channel on our signal will be. Okay. Second thing is that we have to consider the delay, very seriously, the delay constraints of our system, because the delay constraint determine the criterion, the optimality criterion that we should follow to design a code or to evaluate the performance of a code. If we don't have any delay constraint, then we have independent fading on each component, and the performance will be dictated by the Hamming distance. If we have delay constraint, then the Hamming distance may not be relevant, and we may resort to analyzing the block Hamming distance. So that will be the optimality criterion for our code. Capacity also should be defined in a different way for ergodic channel, in which we have a standard Shannon capacity, or non-ergodic channel, in which the capacity has to be considered as the maximum rate of transmission, of reliable transmission, once we accept a certain outage probability. This is the probability that our code will be lost. I think that, no, we still have another 15 minutes, so I can start with the next topic, which is the representation of code. So now we have two sections devoted to the description of channel of codes, and consequently the ways of decoding them. Now, the first section deals with the codes over trellises. This is the, I assume that many, or if not most of you, are familiar with convolutional code, so you know how a convolutional code can be described through a trellis. And we'll see that essentially all codes can be described through trellises, and consequently they can be decoded by using a Viterbi algorithm. So we are using the Viterbi algorithm for optimum decoding. Notice that, if this has escaped you for the moment, that we are not considering algebraic decoding. We are considering optimum decoding. We are considering maximum likelihood. The demodulation rule, the minimum distance rule, is the maximum likelihood rule, and all this decoding algorithm that I'm going to describe today and tomorrow refer to optimum, the maximum likelihood decoding. You may remember that the difference between the hard decoding and the standard algebraic decoding and maximum likelihood decoding is about 2 dB. So we might not be able to lose this couple of dB just because of the simplicity of the decoding algorithm. On the other hand, the maximum likelihood decoding algorithm is generally more complicated than algebraic decoding. So we need ways of overcoming this difficulty. And the two ways refer to a specific representation of code. So today we'll see how we can represent the code using a trellis and consequently demodulate, do maximum likelihood demodulation over the trellis. Tomorrow we'll see how you can do the same using so-called factor graphs and do maximum likelihood or maximum a posteriori demodulation on factor graph. The goal is essentially to exploit the optimality intrinsic in maximum likelihood decoding by skipping algebraic decoding that entails a considerable loss of performance. So codes over trellises. Okay, just to motivate motivate better what I have said a minute ago, let's consider a very simple example: an additive white Gaussian noise channel and a binary repetition code, which means that we have two possible code words, one that is made by three positive one-dimensional signals, and one made by three negative one-dimensional signals. That's the so-called binary repetition code. We have only two code words, and consequently one bit tells the whole story. We transmit a symbol 0 by sending these three waveforms, a symbol 1 by sending these three waveforms. Okay, now, assume that we have transmitted this code word, plus, 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 and we have received 0.8 minus 0.1 minus 0.2 on an additive white Gaussian noise channel. Well, the hard decoding, if you are familiar with it, operates in this way. It demodulates this. So it is, okay, this is positive, this corresponds to a plus. This is negative, it corresponds to a minus. Negative, it corresponds to a minus. So we have plus, minus, minus. Okay, there is something wrong here. We know that the channel has introduced some error because plus, minus, minus is not a code word. So we have to reduce this to a code word. Okay, one way of deciding is to majority vote. So we have 2 votes for the minus and 1 vote for the plus. So we decide for the minus, and we decide that the channel has introduced one error, and the transmitted word was minus, 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 which is wrong because we have transmitted the other one. Okay. So hard decoding is simple to perform, but it's prone to error, more prone to errors than maximum likelihood decoding that I'm going to show you in a second. I will discuss that again tomorrow, but for the moment it suffices to say that to understand that the suboptimality comes from the fact that we are doing our decoding in 2 steps, independent steps. First, we demodulate each symbol without any regard to the structure of the code. And then, after the demodulator has made mistakes, then we try to correct them by using the structure of the code. So we are here, we are disregarding some information. We are doing a decision here without taking into account the structure of the code. And this is wrong. Tomorrow I'll return on this point. But anyway, hard decoding in this case generates an error. Now let's do soft decoding. Soft decoding consists of saying what I have received here is a vector with these components, and I should compare, in the sense that computing the distance between this vector and the 2 vectors that have possibly been transmitted. Okay? This is maximum likelihood decoding. So we compute the Euclidean distance between what we have received, 0.8 minus 0.1 minus 0.2, and this word. We compute the Euclidean distance between this and this word. We compute this, and we discover that this is 2.69, this is 4.69. So we decide in favor of this one, because it has the minimum Euclidean distance. In this case, we don't make any mistake. So there are cases in which, many cases of course, in which the suboptimum decision rule yields the correct result, but there are many cases in which the result are improved if we use soft decoding instead, optimum decoding instead of algebraic decoding. And actually, we know that maximum likely decoding minimizes the probability of error. So no surprise that this happens. And as I said before, we lose essentially a couple of dB from hard decoding to soft decoding. This is why we are considering only soft decoding here. And the problem is the soft decoding, the brute force soft decoding is definitely, you can see from here, that the brute force soft decoding entails computing all this, while hard decoding entails computing some very simple quantity, simply computing the polarity of the symbol that we received, and then comparing what we have with the structure of the code. Much, much simpler than maximum likelihood decoding. That's the reason why we want to resort to some representation of the code that make soft decoding doable without the increase of complexity, considerable increase of complexity entailed by the brute force algorithm, computation of all distances. Actually, consider this brief history of decoding in 3 slides. Algebraic coding theory works in the way that I showed you in the first example. We have a demodulator here that takes the components of a vector that are, each one of the components is a waveform. Okay, demodulate the waveform by saying, okay, this waveform corresponds to symbols 0, 1. The other waveform corresponds to symbol 0, 0, and so forth. At this point, the structure of the actual waveform is forgotten in favor of the symbols that are represented by each waveform. Then the set of symbols is sent to so-called algebraic decoders. Algebraic decoder looks at the set of symbols. It says, is this a code word or not? If it's a code word, it's accepted and everything is fine. If it's not a code word, the algebraic decoder tries to correct the errors introduced by the demodulator. This is called algebraic coding theory or error correction code. Error correction code because the demodulator makes error that the algebraic decoder is supposed to correct. Is there a better way of operating? The answer is yes. This is a good statement by Viterbi. He said the solution is not optimum because we have discarded information prematurely. We have made decision. We have forced the demodulator to make decision without knowing, without taking into account the structure of the algebraic code, the structure of the code. So we have discarded information here. And this information could be useful to make a optimum decision. What kind of information we have discarded here? Well, notice that we have that 0.8. This is very close to 1. You know, this it means that we have had a small amount of noise. But minus 0.1 is very close to 0, which means that the decision that this is a negative quantity is less reliable than the decision that this is a positive quantity. Because 0.1 means that we have a considerable amount of noise, and between 0.1 and plus and minus 0.1, there is a small difference. So this information, this decision is reliable. This decision and this decision are not quite reliable. And we can compensate the unreliability of this and this by taking into account that this is quite reliable. Okay? But if we do hard decoding, we disregard this information. 0.8 is transformed into plus, minus 0.1 is transformed into 1, and minus 0.2 into minus 1 again, without regard on the fact that this decision are unreliable and this is reliable. So this is why basically the error correction covering algebraic decoding is not optimal, because the demodulator makes hard decisions decision that cannot be recovered anymore, and the algebraic decoding has to compensate for the imperfection of the demodulator choices. What can we do? Well, the optimum solution is that leads to a theory that is better to call error control code instead of error correction code. Consists of computing here the metric, that is extracting from the channel output all the relevant information without losing anything. We extract only the information that we need for so-called sufficient statistics, if you prefer, the information that we need to make a maximum likelihood detection. So this is the first device, a metric computer, something that extracts the relevant information without losing anything. At this point, the whole set of data are sent through the maximum likelihood decoder, and the maximum likelihood decoder makes the decision. This is the optimum solution, error control. The point is that the computation of the metric and the decision of the operation of this block may be complex. So we want to make them as simple as possible while keeping the optimality of the decoding process. So if we want to compute the metric exhaustively, the metric in our model are the distances between what we receive and what we have possibly transmitted. If we want to solve it exhaustively, compute all the distances, etc., we have a complexity that is usually not acceptable. If we have millions of code words, we should compute millions of distances for every symbol that we receive, every word that we receive, and this is not doable. This is why we want to introduce in the code a structure, particularly a description, that makes the soft decoding amenable to practical application with a limited complexity. And the solution that I mentioned before are graphical representation. Two representation. Now, one representation is well known and it's conducive to solution by Viterbi algorithm is the trellis, the famous solution for convolutional code, but we shall see that we can also apply it to block code for any code, or tenor graph or factor graphs. What is a trellis? Let's forget for a moment, let's forget about convolutional codes and let's consider the general formulation of the decoding problem or a representation of a code through a trellis. What is a trellis? A trellis is a graphical representation such that there is a one-to-one correspondence between all code words and the path through the trellis from an initial node here and the final node through a number of stages that represent the order of the symbol in the code word, or if you prefer, represent time, if we think of a code word as a sequence of symbols transmitted in time. So if we have a binary repetition block code that is a code having only two code words, the all 0 or the all 1, okay, this is a simple trellis in which we have two paths, 0, 0, etc., 0, 0, and 1, 1, 1, 1, 1. Okay, this is an example of a trellis representing the repetition code. Another example, slightly more sophisticated, is a so-called single parity check block code. Single parity check code is a code that has a certain number of code words characterized by this property. The number of ones in the n tuple is even. Okay? We can represent this code on a trellis like this. Okay, for example, the all 0 code word, a code word that has only two ones. First component and the second components are 1, and then all components are 0, and so forth. If you go through this trellis, you discover that any code word is represented by a path from the origin of the trellis to the end of the trellis, and all paths have an even number of ones. So this is another example of a trellis representing a code. We may think of a periodic trellis, this trellis such that all stages have the same structure, which simplifies the decoding, as we shall see in a moment when we discuss the Viterbi algorithm. If we do this, if we define a code on a periodic trellis, we generate what are called a convolutional code. Okay, convolutional code is a code defined on a periodic trellis. But we don't need to have a periodic trellis. This is another example of a trellis which is not periodic, a code known as 844 Reed-Muller code. And the Reed-Muller code is represented by, has code words that have a one-to-one correspondence with the all paths leading from the initial node to the final node. So we can represent the code by a trellis whose path from the beginning to the end are labeled with the symbols of the code. Maybe, again, it may be periodic, in which case we have convolutional code. It may not be periodic, we have a block code or whatever. Why are trellises interesting? The trellises are interesting because we can do maximum likelihood decoding by using a relatively simple algorithm known as Viterbi algorithm. Viterbi algorithm was designed for convolutional code, is a code represented by a periodic trellis, but we don't have to do this, and we don't have to restrict application of Viterbi algorithm to convolutional code. Any code can be decoded using the Viterbi algorithm, provided that we have a simple enough trellis structure. Let me derive very quickly the Viterbi algorithm. Okay, we want to do maximum likelihood decoding. This consists of computing, maximizing in a general memoryless channel described by this probability density function, the density function of y received vector given x, and the maximization of this is maximum likelihood decoding. In the special case of an additive wide Gaussian noise channel, maximization of this is equivalent to minimizing the Euclidean distance. In the case of Rayleigh fading channel, this is equivalent to minimizing the distance between y and Rx, if you remember, and so forth. If we have a stationary memoryless channel, or in other words, if the probability that, having transmitted x, we observe y at the channel output, is given by this product. This means that every single component of the transmitted vector is transformed into a single component of the received vector independently of the other component. Has no memory. Okay? Every transmitted symbol retains its own individuality when it's transformed through the channel. The channel does not take into account what happened to the previous symbols. It doesn't take into account what happens to the further symbols. It treats every symbol independently. So the stationary memoryless channel is like this. Okay, in this case, if we take this rule again, maximization of P, and we observe that P is equal to a product, we may observe that maximizing this is tantamount to maximize the logarithm of the product, the sum of logarithms. And consequently, for a stationary memoryless channel, the quantity that we have to maximize to do maximum likelihood decoding is the sum. Again, for example, for additive wide Gaussian noise channel, P is an exponential function, and the logarithm turns out to be a logarithm of a constant, is relevant constant, minus the sum of the square of the difference of the components. And consequently maximizes this, it tantamount to minimizing this Euclidean distance. Now, if x, the vector x, corresponds to a path to the trellis, or in other words, if we have represented our code using a trellis, then maximum likelihood decoding can be interpreted in this way. We want to find a code with a consequent trellis path such that this sum is minimum. Okay? Remember that we have to minimize this, and constant, since n0 is a constant, we can disregard it. And for additive wide Gaussian noise channel, we need to find the path such that this sum is minimum. Remember, xi label the edges of the trellis, y sub I are observed. So what we have to do is to observe vector y, compare vector y with the labels of the trellis, compute for each branch, for each edge, this quantity, y sub I minus x sub I square, and find the path to the trellis such that the sum is minimum, so-called minimum length path. So for example, consider this path. What is the accumulated sum or the metric corresponding to this path? This path has label x1, x2, x3, x4, and x5. We observe y1, y2, y3, y4, and y5, and consequently we can associate to each one of these branches one of these values. So this will be y1 minus x1 magnitude square, etc. And we sum up these quantities through this path, and we have the metric corresponding to this path. We have to choose the minimum path, the minimum metric path. Of course, we cannot do it. I mean, it doesn't make any sense to use a trellis if we do a brute force approximation. In other words, if we compute this quantity for each path, we want to avoid the brute force calculation of all metrics for all paths, because otherwise there is no point in using a trellis. Now enter Viterbi algorithm. Viterbi algorithm is a very simple algorithm that is based on the trellis structure of the code representation, whose goal is to compute this quantity and minimize it without resorting to the brute force evaluation of all metrics for all paths. This is a most efficient algorithm. The basic step of the Viterbi algorithm is called the add, compare, select. And what we do is the following. Suppose that for the moment, and then I will show you how these are computed, that we have this section of the trellis, and we have this accumulated matrix here at this node. Then suppose that from each node we move to the next node by this path, whose metric will be on 1, this 6, this 4, and so forth. Okay, add step consists of the following. For each arrival node, we compute the sum of this quantity and the label of the branch. So this will be 3 plus 1, 3, and 1 plus 4. So the two branches leading to this node. 3 plus 1 or 1 plus 4. And it's 4 and 5. Then we compare. We take the maximum between 4 and 5, and we choose 5, which means that we disregard the branch having the smaller value of accumulated measure. So we remove this from consideration, and we keep only this one. Also in this case, we consider this node. We consider the branches leading to this node. 3 plus 6 will be 9. 3 plus 1 will be 4. We consider only 9, and we remove the other one. Here in this case, we remove this path. And in this case, we remove the path. Okay, so we have reduced the structure of the trellis, and we don't have to consider any further the path, including those that we have removed from consideration. The value that we have obtained after comparison are the values that we associate to the new branches. Then we extend the trellis by one step, and we repeat the procedure. Well, we can pick the maximum of the minimum. It depends on the fact that you consider plus or minus the quantity. That can be done for maximization, for minimization. It's totally irrelevant. Okay, so this is what Viterbi algorithm. And once we have finished doing this, and this is done in the simplest possible and the most efficient way, we have selected the path with the best metric, and consequently the path corresponding to maximum likelihood code word. So we have a complexity that instead of increasing exponentially with the length of the word, as we do with the brute force approach, it increases only linearly with the block code. On the other hand, it increases with the number of trellis states. The trellis state, in this case, is the number of add, compare, select that we have to consider. Consider again the three examples that I've shown before. Here we see that the maximum number of add, compare, select at each time will be 4, because we have 4 states. Consequently, 4 add, compare, select operation to be done here, 4 here, 4 here. So this reflects the complexity of the algorithm, and the complexity is also related to the number of trellis stages that we have here. So it will be 4 in terms of states and 4 in terms of complexity of length. Here we have 4, here we have 2, and here we have 2 again. So since the block length and the number of trellis states depends on the code, we would like to choose the code. Among the different codes, those have the minimum complexity. In general, there is very little to do about n. As we increase n, we increase the performance. So the longer n, the better, if we are allowed to do that. So what we have to do is to try to minimize the number of trellis states. So let's consider this problem. Suppose that we have one code. We want to represent it in the form of a trellis in order to be able to apply the Viterbi algorithm. There are different trellis description for every code. We want to choose the one with the minimum complexity. So the problem that we are faced to is how to generate a minimal trellis code, a minimal trellis representation for a given code. This is a major importance. So we are given a code. We are chosen a code according to certain criteria. We decide that we want to do maximum likelihood decoding. We choose trellis representation. So the first step will be, okay, let's find the trellis representation with the minimum number of states, because this will allow us to do optimum Viterbi decoding with the minimum complexity. So right now we take a break, and then we consider how to minimize the trellis complexity and consequently the decoding complexity for a given code. Okay, we'll resume between 20 minutes.
I have a question about interleaving.
Yes.
So by doing